As we continue with our application of linear systems, solving for two unknowns with two equations. The vending machine contains dimes and quarters. The number of quarters is 7 more than twice the number of dimes. The coins have a total value of $20.35. How many of each coin are there? How many of each coin are there tells us how to set up our let statements. So let, let's say D represent or be the number of dimes. Remember that dimes are worth 10 cents or $0.10. Now let Q be the number, the actual physical number of quarters. Remember that quarters are worth $0.25 or 25 cents. So from the information here, the number of quarters is 7 more than twice the number of dimes. So from that, we know that there is more quarters than dimes. So equation 1, quarters, there is 7 more than twice the number, that's 2 times the number of dimes. Now the second equation is their total value. Is 20.35. So if we think about 10 cents times how many dimes, it's how much money we have in dimes, and 25 cents times how many quarters is how much money we have in quarters. When we add that together, the total is going to be 20.35. So again, how much is a dime worth times how many dimes there are, added to how much a quarter is worth times how many quarters there are, and all that will equal 20.35. And there's our second equation. Now we go about, as we usually did, solving by substitution or elimination. This is already rearranged to isolate the number of quarters. So I'm going to take that and I'm going to sub it in. So equation 1 into equation 2. Now let's distribute and solve. So 0.25 times 2. 0.25 times 7. Let's collect like terms. $20.35, take away $1.75, $18.60. And now we know that there's actually 31 dimes. We take what we found, substitute it back into one of the original equations. And show our load bearing steps. We think about how many we have. There's our solution. The machine, therefore, we ever want to check, we could then again substitute these values in to see if it works. 31 times 10 cents, $3.10. 69 times 25 cents, $17.25. When we add those together, we have 20, 35. That's essentially that equation right there. It works out. We are correct. Awesome. The difficult part is remembering that it's what it's worth times how many we have. So let's do a second example. We need 200 milliliters of 74% concentration cranberry juice. To make that mixture, we have 10%, there it is, 10% cranberry juice, and 90%. If we mix them 50-50, it wouldn't be 75 or 74% concentration. So it's the same sort of thing, it's how much it's worth, or the concentration this time instead of the actual dollar value of a coin. So how much of each kind of juice? So this one's a little bit more wordy, but let's say X be the amount of, say, 10% juice needed. Let Y be the amount of 9% juice needed. So again, we have a total 200 milliliters. So first equation, X plus Y, 200 milliliters. Our second equation is the concentration. If we think about the 10% mixture times how much we actually add is going to be mixed with the 90% concentration times how much we add, and all of that is going to equal 74% concentration, but it's times the 200 because that's how much will actually be there. I did the top one by substitution. Let's do this one by elimination. If I want to eliminate, let's say I want to eliminate the Y, I do equation 1 times 0.9. $200 times 0.9, 180. This equation, I'm just going to simplify that number, so let's slide it over. 0.74 times 200, 148. Same coefficient for the Y, same sign, so we're going to subtract. 0.9, take away 0.1, 0.8. 0.9 take away positive 0.9y, 0. 180 take away 148. Solve for our unknown. Again, what does that represent? That's how many milliliters of the 10% concentration juice we're going to use to make our full mixture. Show the math, even though you should be able to do this in your head. And now we've completed. We have our solution. Therefore, Stoica should mix 40 milliliters of 10% solution with 160 milliliters of the 90% solution or juice. Nice. Okay, flip the page. Let's just think about the next two. I'm going to let you do them, but let's just look at them together. Alex is 9 times the age of his son. In 3 years, he'll be 5 times the age of his son. This one always confuses people. I just want to help you out. So let statements. Let's say let X be Alex's age right now. Let Y be his son's age. And again, that's right now. So if we look right now Alex is 9 times the age of his son. So again, Alex is older than his son. That means that Alex is going to be equal to 9 times the age of his son. Now, in 3 years, he'll be 5 times the age of his son. Alex is still going to be older. He'll still be older. So he'll be 5 times the age of his son. But in 3 years, his son will be 3 years older. Now we think about that will be 5 times. We also need to remember that in 3 years, Alex is also going to be 3 years older than he is right now. Now that we have 2 equations, we can go ahead and solve. When we look at the 4th example, the same sort of thing. If you want to try it without seeing, go for it. But again, once we write our let statements, increase sales, the store manager mixes gummy worms. Let's call that at 160 per kilogram with chocolate swirls. The new price is $175. How much of each type of candy will we need to obtain 50 kilograms? So kilogram, we're all good. But again, equation 1 is going to be the amount of gummy worms, and the amount of chocolate swirls is going to equal 50 kilograms. The second one is the weight. So we have gummy worms is $1.60, and chocolate swirls is $2.20. So just like the concentration, we're going to have the actual price per weight of gummy worms plus the price per weight of chocolate swirls times, again, how many chocolate swirls, the weight of chocolate swirls. It's going to equal that selling price, but don't forget, times how much there will actually be, 50 kilograms. And now we have our 2 equations. Again, for sake of time, I haven't done let statements, I haven't solved, but you can see your setup there. After you complete these, try some practice of writing out the equations.